In section 5.3, you learn a few different techniques for solving systems of linear equations algebraically. I've taken a screenshot here of a couple of those different techniques, but you can read more about this by either pausing the video or go into the e-text or physical text and reading these as well. What I really want to show you in this video is how you can apply that through some examples. So let's look at this example here where we're asked to solve a system algebraically using what's called the substitution method. Notice that equation 1 has already been solved for x. It has a variable isolated. Usually in this case, if you were to be able to pick from all the different methods, substitution would kind of stick out as a good choice because one of the variables has already been solved for. So what we can do is substitute equation 1 into equation 2. In other words, where I see x equals 2y plus 1, I can replace x with 2y plus 1 in the second equation, like so. At that point, you have a linear equation with one variable. So you distribute the 2. You can then subtract this constant 2 from both sides. Combine the like terms that are on left and right sides separately. So 4y minus 3, y becomes y, and 4 minus 2 becomes 2. Next, you're going to take that answer, y equals 2, and substitute the 2 into the equation for y into one of the two equations. So for the purpose of this example, I'm just going to use equation number 1. And where I see the y, I'm going to replace it with a 2. When we work that out, we get x equals 5. So the solution to the systems of equations is the point 5, 2. Make sure that you're putting these in the correct order if you're asked to write them as an ordered pair, because x equals 5 means that the x coordinate is 5. Just because that you solve for y first doesn't mean that it appears first in that solution. You could also list them separately. You may be even asked to list them separately like this. And you can confirm this with a graph. Next, let's look at another algebraic method for solving systems, which is the addition method. Notice the y coefficients are the same value but opposites, -1 and +1. Same number, different signs. This is a clue that this addition method may be the best method for solving the systems of equations algebraically. So what we do in this method is we take each equation and we add them together. We are adding together equations 1 and 2. 2x plus x becomes 3x. -y plus y becomes 0. And 7 plus 2 becomes 9. At that point, you have an equation with one variable. By dividing both sides by 3, you get x equals 3. Now that you have one of the answers, you can substitute this answer into one of the equations. So I'm going to choose here to substitute this x equals 3 into equation 2. So instead of writing x plus y equals 2, I have 3 plus y equals 2. Solving for y by subtracting 3 on both sides, I will get y equals -1. So the solution is the point 3, -1, or you may be asked to list those separately. And just to verify, here is the graph and the point of intersection. The last algebraic technique presented to us in this section of our text is the subtraction method. Look at the x coefficients and notice how they are different numbers and different signs. Actually, the same is true for the y coefficients. This may mean that subtraction is a better method to use. Again, it's not necessarily the only method to use, but it is kind of set up, I guess you could say, for subtraction to be a little bit easier. So what we want to do is we want to make these numbers match, and then we want to subtract our equations one from the other. So to make the numbers match, we need to multiply this 3 by 5 and this 5 by 3, thus getting 15x and 15x. Well, if I multiply this term by 5, I've got to multiply everything in the equation by 5. So that's why you see here in red, equation 1 times 5. So notice every term gets multiplied by 5 to get this new equation. Every term in equation 2 gets multiplied by 3 to get this new equation. Then here is where the subtraction comes in. 15x minus 15x is 0. Be careful, negative 20y minus negative 18y is negative 2y. And 35 minus 3 is 32. At that point, you have an equation in one variable. I can divide both sides by negative 2, and I get that y is negative 16. Like the other examples, once you have one of the pieces, you substitute it into one of the other equations. Here, we're just going to choose equation 1 to substitute y equals negative 16. So notice how y is now being replaced with negative 16. We would multiply that together. We would subtract that constant from both sides. Then we would divide both sides by 3, and we should end up with x is negative 19. So the solution to the system is this coordinate pair, or ordered pair, negative 19, negative 16, or you can list those values separately, and you see how this matches the graphical representation with the point of intersection at negative 19, negative 16.